Okay, thank you very much for inviting me here today. My name is Dr. Barbara Giles, and I work with the Science Mission Directorate at NASA headquarters. I've been working recently with Mary Beth Adine for an announcement of opportunity that we're going to release in the fall for both full missions supported by the Science Mission Directorate, but also for missions of opportunity that could be proposed to the International Space Station. So tomorrow I'll be talking about that announcement of opportunity in more detail. Right now, what I want to talk about, though, is the broader interests of the Science Mission Directorate. And if you want to field science experiments to the space station that would be supported by the Science Mission Directorate, is there a map? Is there a way of being successful doing that? So I hope to give an introduction to that. So the next slide talks about, there's been science talked about all day today, and it's kind of interesting that there's one directorate at NASA called the Science Mission Directorate. Is this the only place science is done? Of course it's not. But in this case, the Science Mission Directorate does science in 4 distinct areas. Certainly advancing Earth system science to meet the challenge of climate change, understand the sun and its interactions with the Earth and the solar system, to look at the history of the solar system and how it formed, and to discover how the universe works, how it began, how it evolved, and to look at the question of are we alone? The next slide talks about the strategy that the Science Mission Directorate follows pretty rigorously in deciding how it's going to go about its business. And certainly at the very top of the list is pursuing answers to big science questions. There's a lot of different kinds of experiments that can be done. If it's not a breakthrough experiment, if it's not looking at very large fundamental questions, it's not at the top priority of the Science Mission Directorate in general. And we also look at experiments from which the view from space is a defining contribution. If something could just as well be done from the ground, we tend to let it be done from the ground. The next thing that's important is that we do this by putting programs together that accomplish this science within the budget. We're very budget conscious. There's no lack of good ideas, and well, we're as good as anyone else at staying in our budget, but this is one of our defining strategies. When I say that we define programs to do this, like I said, there's 4 science areas. One thing that you're going to find during this talk that's a little bit difficult to absorb, but that's why we want to give you this map, is that there's not going to be one place and one time to propose experiments to the International Space Station. There's a whole variety of programs that have been in place for a long time that have their own goals, and they're going to be having opportunities announced at different times. So I hope to give you an introduction to that, and that as time goes on, you'll keep looking for all of those different opportunities. Certainly, we want to partner with other agencies. We like to mature our technologies before we need them. And of course, sharing the results and the story of what we do is very important. The next slide is how we make choices. These are the principles. Certainly, we need to make progress on all 4 science areas. That's what we call our measure of success. All the choices in the end, if you look at all of the announcements that come out, the choices are based on scientific merit, by peer review and open competition. Certainly we want to partner. Certainly we don't want to duplicate the efforts of others. That balanced portfolio is something that comes into our investment choices. And certainly, because this is about a $5 billion a year effort, we recognize that this is a very important investment of taxpayer dollars. This science enterprise is something we recognize we must be very open and accountable and transparent. So, as I mentioned, there are 4 areas, $5 billion a year. About $1.8 billion is devoted to earth science, about $1.5 to planetary, about $1 billion to astrophysics, and about $650 million to heliophysics. And so remember, I warned you that this is all divided up into different programs. Let's look at what some of those programs are. It's not in the next slide. The next slide, sorry. I didn't say next slide to the back. But just over the past 12 months, here are some of the major missions that we have deployed or that have reached milestones across the solar system. In astrophysics, WISE was launched. SOFIA, which is an airborne system, saw first light. In earth science, our partnership with NOAA, we deployed GOS-O, GOS-P. In heliophysics, we launched the Solar Dynamics Observatory. In planetary science, the milestones for missions that are out in the solar system are that Messenger flew by Mercury again. Cassini has flybys of Titan and Helen. The next 2 slides are coming up in the future. What missions are we launching in the future? The next slide shows the next 12 months. Again, the airborne system in astrophysics has its first early science flights. In earth science, we will launch GLORY and Aquarius. In planetary, we've got several encounters with asteroids and other objects. Messenger will actually enter orbit around Mercury for an extended period of time. After that, what else are we doing? New Star is going to launch for astrophysics. Earth science, NPP, and of course that says not earlier than, schedule's starting to get a little fuzzy there. RBSP for the heliophysics, that's a radiation belt probe. In planetary science, again, there's several launches in planetary science, and again, some other encounters. Dawn will be encountering Vespa. Juno will launch. Grail will launch. MSL. That's going to be a very busy time for planetary science. So a lot of missions on the horizon. Now let's look at, I believe the next slide are those programs I was talking about that I want you to understand, is that as time goes on, any one of these blocks, any one of these programs in SMD could decide that as part of their science endeavor, that fielding experiments at the space station may be an important part of their portfolio. And in the next year, I have already counted 7 of these blocks, which we'll talk about tomorrow in detail, that will have open opportunities. And so understanding over time what the goals of each division are, what the goals of each program are, how they've laid out their science plan for the future, and how any experiment that you would like to deploy, how would that fit in? You're going to have to find your spot in the map. And I'm going to tell you, this is written down, so there's a resource you can go to at the end. But the 7 items that will come up in the next year is under the planetary division, the Planetary Science Research block, right there in the middle. They have an open NRA now. In Earth Science, the Earth Science Research Block, there's an open NRA. And next year, it'll be Earth Venture that will have an announcement of opportunity. Under Astrophysics, Astrophysics Research, an open NRA. In Heliophysics, it is the Heliophysics Research, open NRA. And then for Astrophysics Explorer and Heliophysics Explorer, that's an announcement of opportunity that's coming out this fall that we'll talk about in detail tomorrow. But we really have to understand our place here, and that's what I think is a little bit difficult. So let me go one more level of detail. All of these different programs have scientific goals, and they also already have a lot of assets in place and assets planned to meet those goals. So for new experiments, where would you fit into that mix? It's important to understand that. The next slide shows you how big that program is. I know it's a bit of an eye chart. You don't have to look at everything. At the very top, notice that among these 4 divisions, there are 87 missions that are being supported right now that use 100 spacecraft around the Earth. And you'll see that for the different divisions, astrophysics, earth science, heliophysics, planetary, those are all the different colors at the bottom and all the different mission names. And so as time goes on, when you want to plan a concept to propose, you want to understand what is in extended operations. That's something that's already up there. It's been making contributions. It has a plan to keep doing those contributions. What's in the primary mission phase? What are those already contributing to the system? There's another 17 missions in the implementation phase right now. Another 12 in formulation, and at the bottom you'll notice there's another 10 or 11 down there that are being thought of to get on the chart. And so for new concepts, how do you fit into that science picture for any given program? Successful proposers are going to understand that and complement or extend, but not duplicate. I have to tell you right now, whenever there is an announcement of opportunity, there's just no lack of good mission ideas. In fact, there's an excess of wonderful ideas that we don't have the budget to go forward with. So proposers, successful proposers have more than just a great idea. They also have a concept that is also vital and urgent to the overall plans of that particular program that they're proposing to. Let's go on to the next chart. Now I just want to spend a few minutes for each of those 4 divisions. First, just giving you their overall science focus, and then just a few little notes about each of those divisions. So if you're interested in doing investigations for the Earth Science Division, certainly the important questions, how is the global Earth system changing? And that word global is not accidental. Local experiments are not considered to be as high priority, even though there are some that are supported. What are the sources of change in the Earth system? How will the Earth system change in the future? And how will the Earth system science, how can the science that this directorate is supporting, how can that be used to improve the mitigation and adaptation to global change? As the next slide shows what is called the A-train for Earth science. And hopefully that's a concept you're really familiar with if you want to propose Earth science. The A-train formation allows for coordinated measurements. Instead of putting every instrument known to man on one platform, we put them on several smaller platforms and fly them in a close formation, so that the data from the several satellites are used together to get some comprehensive information, especially on atmospheric components. Scientists are able to gain a better understanding of the important components of global change, and you'll notice that this particular rendition of the A-train includes some assets that are coming up in the future. Notice that says OCO-2. OCO, as you may remember, was not successfully launched, but we will be building that again. And so certainly as you go forward thinking about how you might propose an earth science experiment to be hosted at the space station is how can you complement or extend the A-train. Here's the next slide is a kind of a recent and practical example of using the A-train and some other types of measurements. And this is just high spectral resolution LIDAR data. And looking at the Gulf region, it is not unusual for the science missions supported by the Science Mission Directorate to also look at practical matters on Earth when the time is needed. So here, when LIDAR hits an oil patch, and you'll see there's several different measurements all focused on the same oil patch. But when the LIDAR hits an oil patch, it will reflect in a different way than it does when it hits open water. And so the way that the sun reflects, the way the LIDAR reflects, the idea is that may tell folks how thick and dense the oil is, so that they could track that over time. So successful proposers, as you go forward, will be able to demonstrate how your concept fits within all of these different kinds of assets that are already in place. Are they complementary? Do they support them? Do they provide something that the assets don't already provide? And how also can you participate in solving these vital and urgent problems that face us here on Earth? The next slide is, I find this result just really fascinating. And I'm not quite sure why we had to title this slide the 30th anniversary of Mount St. Helens. But anyway, over time, you'll see these are Landsat images of before and after that big eruption in 1980. Now, the earlier years are red, and the lower ones look more like natural color, and that's only because they were different instruments taking these measurements over time. They're all kind of false colors, so I'm not sure why we couldn't normalize them, but we didn't for this particular slideshow. But you'll notice at the very beginning, if you think of the red as vegetation, which is what they were able to measure there, you'll see before the eruption, vegetation just all over the place except the very summit. And then after the eruption, there was quite a bit of damage. And then as time goes on, after 30 years, the recovery still isn't quite complete. What I really want to talk about here, though, is that these kinds of long-term data records, these are absolutely vital for understanding how elements of the Earth evolves after a large event. And such records exceed the lifetime of any given instrument. We have to replace these instruments that have reached their useful lifetime. And so here's an example where over time, you're using different instruments, but they have been cross-calibrated, they have been deployed in a manner to keep the integrity of the long-term data record. And so successful proposers to earth science initiatives, they're really able to demonstrate how their concept can contribute to that long-term data record for the type of science that they're doing. You know, how can you make sure that that new data can be well cross-calibrated, cross-correlated, and integrated with older data streams, even if you're using different technologies. So that's something that's a high priority for this division. The next slide, this is the last one for Earth science investigations. I wanted to emphasize that there are many different types of platforms and technologies already employed for the initiatives that are top priorities. And here's an example where instead of a permanent orbiting satellite, that it's considered to be more robust and more cost-effective to use an uninhabited aerial system. And in this case, for hurricanes, which are just periodic and in a particular place, overflights tended to be the thing that they think is the most effective way of looking at that. And it looks here like an investment of $29 million over 5 years should give data sets on, let's see, it said what number of hurricanes, 9 to 12 hurricanes. And so that's going to be a very nice data set to advance understanding of that particular phenomenon. So again, successful proposers will have a good understanding of what investigations are already being supported across that particular endeavor, and understand, should it be done in campaign mode? Should it be done with an orbiting platform? There's a lot of really good proposal ideas that could well be eclipsed by another good idea that's just already being supported. So you're really going to want to do your research to address those. Let's go on to planetary science. Now, the questions for planetary science, the inventory of solar system bodies, how did these bodies evolve? How did they originate? What are their characteristics? How could life begin? And what are the characteristics of bodies that may pose a hazard? These are the priorities for the planetary science division. And let's go on to the next slide. It may be difficult to imagine how the space station could be useful for planetary science efforts. I mean, this division is focused on, well, planets elsewhere, and certainly most of the time we send our satellites there to study them. But when you really think about it, it is a very large investment, both in time and money and effort, to send a satellite so far out into our solar system. The instruments that we deploy, and we put as many of them on the spacecraft as we can, but every one of those have to work. And so maturing instrument technologies to the appropriate TRL levels before we try to deploy them, that's one of our strategies. Doing that here near the Earth is where, at least for the planetary science division, they believe the space station could be helpful with. So please think of that. I just leave this as a really neat kind of result. The next result on the next slide is also kind of entertaining, I think. The Planetary Science Division at headquarters does accept proposals for concepts at the International Space Station. And successful proposers are going to be able to demonstrate how their concepts enable the science priorities of this division, which could be technology development related. Certainly high-resolution imaging, and I don't know if that's the highest resolution I've ever seen, that particular image. It looks a little fuzzy to me right now, but I think that's just a display issue. High-resolution imaging and the dynamic control of those instruments is really an important focus. We want to understand the electrodynamic environment of these planets. We want to understand their atmospheres and their ionospheres. Maturing that here at Earth is something considered to be worth doing. The very last one for planetary science, I just left this in here because I just thought it was really interesting. So we'll just have this as a little treat in the middle of my talk. And this is about the Phoenix lander. In 2008, Phoenix ended up being, it went into Martian winter and gets encased in ice, and you hope after winter it thaws out and it's going to communicate with you again, and it didn't. You'll notice up here, this is a really neat picture. This was taken just after Phoenix landed, and the bright spot in the middle is kind of the main body of the spacecraft, and then there's two little mouse ears. Those are the solar panels sticking out. And so later, after we weren't able to contact it after that winter, we managed to get some assets in place to take another high-resolution image down here in the corner. You may not be able to see it, but you'll want to look at it later. And you'll notice, there's kind of the main body in the middle, and it's not very bright anymore. It's not reflecting sunlight very much anymore. And in fact, it seems to be absorbing in a way that it's covered in dust, and the solar panels seem to be missing. It's thought by looking at this image that one's laying on the ground and one's folded under. Heliosphere respond, and what are the impacts of space weather on humanity? So one thing I think about when we think about exploring in the cosmos, going back to the moon, going to Mars, I think of it like, hey, I'm going to go camp on the beach. If I'm going to go camp on the beach, I want to know what the weather is. If it rains, I'll be kind of fine, but I won't be as productive, perhaps. Might even be uncomfortable. If there's going to be a hurricane, I really need to know that. So when we talk about understanding the sun and its impact, not just on Earth, but on other bodies in the solar system that we may go to, we need to understand and have situational awareness of what our environment is. And that's what this particular division's science focuses on. There are quite a few heliophysics spacecraft in orbit right now. In fact, I think there's 16 missions, and I have to admit now I've lost track of how many individual spacecraft, and this is my division. But the next slide shows recent results of our very latest one, and that's Solar Dynamics Observatory. And I've given you a website here where you can get some of the latest results. SDO is going to help us understand the sun's influence on Earth, near-Earth space, and it does that by studying just the solar atmosphere, but it does it on such tiny scale sizes, both spatial and temporal, and in many wavelengths, that we're seeing things on the sun that we've never seen before. The next slide shows you an example by zeroing in on that one spot on the sun. And in this case, there's actually several sets of measurements overlaid on there. So first of all, you see the magnetic field. You can kind of see magnetic field lines traced out by the plasma. And the plasma is actually radiating in UV light. That's why we can see the plasma in those arcs. In blue and orange, that shows the polarity of the magnetic field and shows us something about the strength of it. And so being able to put these together is showing us that, that these plumes of plasma are originating from very strong regions of magnetic field that emerge from the lower layers in the solar atmosphere. So we're really excited about this. If you go to the website, you can see some very high-resolution movies of this phenomenon, and I tell you, you've never seen the sun look this way. As I mentioned for the next slide, is that we're really interested in space weather, but for the Science Mission Directorate, we're really interested in space weather not from a monitoring point of view. We're interested in understanding how it works so that we can enable other people to do the monitoring. The Science Mission Directorate is about the science of space weather. How can we enable the operational agencies to predict space weather and then use that for the benefit of our economy, our security, and things like that. Let's move on to, let's finish up with astrophysics. And actually, we had a really nice introduction to what this division is interested in the previous presentation when he was talking about fundamental physics and the observational part of that, which is done by the Science Mission Directorate. He was talking about the astrophysics division. And so I think we talked about that in pretty good detail. We won't repeat that. Let me look at the next slide. I just wanted to show you 3 results. This one is really nice. Swift satellite, which is up there now, has been able to resolve a decades-long mystery about why a small percentage of black holes, only about 1% of these black holes, suddenly emits massive amounts of energy. And they have found that these black holes light up, emit all of this energy when galaxies are colliding together. And we care about when galaxies collide because it tells us something about the future of our own Milky Way galaxy. As you may know, our nice Milky Way galaxy is predicted to crash into Andromeda in a few billion years. So we may have a contest between whether our own sun, supernovas, or we collide with Andromeda. We don't know. All I know is that in so many billion years, we're going to have to move. But anyway, back to reality. We've got a few billion years. Theorists have shown that the violence in those mergers can feed a black hole, and this was a theory for a while. Swift was able to give the experimental proof for that. And so as you go forward and you want to propose experiments in the astrophysics area, successful proposals are going to be able to articulate that scientific theory under investigation. What is its importance, and how their experiment might be able to resolve that theory. Okay, let's go on to the next item. Speaking of colliding galaxies, the Galax mission, it discovered a nice tail off the side of this particular galaxy. You see those, the little blue tail there? And there are young stars forming in that tail. Now, when galaxies tangle together, and they're magnetic, there's gravity, there's plasma. They tangle together, they kick dust, they kick gas. And in this case, this little galaxy is not colliding with one other galaxy, it's colliding with the entire Virgo cluster of galaxies. And so the gas from this galaxy is being shoved back into a choppy tail. The turbulence that exists, it's kind of like sand coming off. And so when you want to form young stars, the theory was that the kind of denser gas that you would get was really too heavy to come off and be able to form this kind of tail. But Galax shows that in this case, that heavier star-forming gas really can be pulled out into the wake of a galaxy and perhaps form stars in a swirling eddy back there. And so the astronomers were able to find this. You'll notice on this side we have a visible image. If you just used a regular telescope, this is what you would see. Here we've got ultraviolet observations. And so certainly for astrophysics investigations, using many different wavelengths simultaneously to see things that you can't see otherwise is one of the focus. So successful proposers for astrophysics really need to exploit a wide range wavelengths and other observation techniques, in addition to being able to point at a variety of objects, maintain exposure times, have the resolution to make breakthroughs that this division wants to support. Let's see, I think we've got maybe one more. Let's see. Yeah, this is nice. And this is about when you're using multiple wavelengths, certainly you don't have to do everything from one platform. And this is an example of where the measurements from several different platforms were brought together. Here is just a binary star system. There's a giant red star that is feeding a little white dwarf. And when the white dwarf gets in the wind of the red star, the material from that wind can make a nice accretion disk. And you'll notice up in the top, we've got a superposition of X-ray, radio, and optical data. And I believe there's Hubble data, there's actually Chandra data, and then there's a ground-based data making that up. And you see the little green tail? Okay, so that's gas that's coming off of the white dwarf as it's being pulled around by this wind from the larger red star. Now, this is considered to be a big science question. Where's the big science question? We always go with the big science question because these types of systems, those that depend and influence each other, are likely sources of the types of nebulas that result in type 1a supernovas. And type 1a supernovas, of course, are the ones that you can see from across cosmological distances. So successful astrophysics proposers are going to be able to demonstrate how their concept can work together with all of the other assets that might be in place to answer their important scientific problem. Okay, let's wrap up. The next slide is just a reminder that in addition to the big missions, in addition to deploying hardware in space, on unmanned vehicles, on the space station, wherever it may be, we also have quite a bit of resource dedicated to enable people to just use that data over time, and we call that our research program. And so there are continuously open calls, NRAs, that are looking for scientists to use that data and extend the results of any of these missions. And last, I think, this was almost last. It was just a reminder that certainly there's 1 to 2% of our budget that is always devoted to workforce development, education, and public outreach. There will be opportunities to do this kind of work also using whatever assets there are at the space station. So you'll see that we have an opportunity for that as well tomorrow. And now the last slide is the map. If you are really looking for how to put all of those pieces in place, there is an SMD Science Plan, and I think there's an address here at the bottom that you'll see. This is a brand new plan for 2010 that if it's not posted there right now, if the 2006 plan is still there, the 2010 plan will be posted within the next couple of weeks. I was actually assured I could go ahead and change the cover on this slide, but we'll see if they have it posted. But look for the new plan. This lists all of those different programs. Remember all those different blue boxes that may come out with opportunities? This lists all of them, and hopefully in a way that you can search for and find your particular scientific interest. Okay, thank you very much. Tomorrow we'll talk about specific open opportunities.